Hi, welcome to the 8th lecture on compactness. Today we are going to prove one of the most important results in compactness. The product of two topological spaces is compact with the product topology, of course, if and only if each of the factor spaces is compact. And we will also give applications of this result as usual. Okay, let's get started. So the main result is the following. Let x, y be topological spaces. Then x times y with the product topology is compact if and only if we want make it x tau x, y tau y, if and only if each of the factor spaces x tau x and y tau y is continuous. Okay, this is a theorem, right? So just stop to and think. There is an if and only statement. Most often in if and only statement, one statement will be easier to prove. Most often, not always, of course. Can you guess which part is easy? It follows from some result which we proved yesterday. Do you remember we proved yesterday if f is a continuous function from x to y and if this is compact, then fx is compact. Yeah? Now can you think of this? Okay, so again let us quickly recall. So if x tau x and y tau y, these are the topology spaces, right? The product topology tau on x cross y, okay, the basis for this is sets of the form u cross v, where u is open in tau x and v is open in y, right? This is what, okay, this is a basis for the product topology. Now you know that with respect to the product topology, the natural projections onto the factors, these are continuous, right? xy going to x or xy going to y, from x cross y to y, where x cross y has a product topology, these are continuous. In fact, the product topology on x cross y is the smallest topology, which makes both pi x and pi y simultaneously continuous. Anyway, if you don't know such things, don't worry. Okay, this is all we need. So these are the two facts I want you to remember. Okay, there is another fact also, we will come to that later. Okay, the third fact about product topology is this. Suppose I have another topological space z tau z, and suppose I have a map f from z to x cross y, right? Therefore f of z I can write as f1 of z and f2 of z, and f1 of z takes values in x, f2 of z takes values in y, right? This is a projection. This is nothing other than f1 is pi x composite f, and similarly f2. All right, so if f is continuous, since pi x is continuous, f1 is continuous, similarly f2 is continuous. Conversely, this is an important thing, f is continuous if and only if each of f1 f2 is continuous. Okay, these are the three important facts about product topology, which will be used very, very often. Okay, keep that in mind. Now come back to the thing. So suppose x cross y is compact, then what do I know? Pi x maps x cross y to y, sorry, x cross x to x, and this is onto, and this is continuous. Therefore pi x of x cross y is x, and this is compact, this is continuous, therefore this is compact, and similarly y. So x cross y compact implies x is compact, and similarly y. Okay, so please go through whatever I did now. Please review the facts I said about product topology. Okay, this is the way you have to learn. When you learn through product topology, you might have forgotten. You will be more worried about understanding the theorem and its proof, trying to remember, etc. But what finally one needs is the basic facts and the most importantly used facts of that particular concept. They are the ones which will help you in the long run. Okay, so you should learn how to study also. Okay, right, so one part you have proved. Now the second part is what I want to prove. So assume now hypothesis x y compact. Conclusion, we have to prove this x cross y compact with product topology, right? So how are we going to do? The first thing, okay, before going to do that, let's just do some build up our geometry. Suppose I have a line segment in R2, right? And suppose I cover it by finitely many rectangles. Right, now do you see something very interesting? You must notice, okay, look at the projection of these fellows. The projection is here, and projection of this fellow is here, and projection of this fellow will be this, and projection of this fellow will be, they should be slightly different, so let me just assume it is of this form. Okay, ignore this, right? And similarly you can do on the other side also. You can see these open covers actually cover something very interesting. What do? They cover as actually, yes, I don't know whether it looks better, but yeah, let me do it. Okay, this vertical line, okay, lies in a vertical band, and your finite now collection of rectangles which cover this line segment actually cover a vertical band. Yeah, okay, just try to imagine, because you have to build intuition. Unfortunately, you know, people always work too formal, you see. So think about this. Okay, keep that in mind. So to prove that result, what we want to assume, do you remember we already proved in one of the earlier lectures? Okay, if I want to prove x tau is compact, okay, and if B is a basis for tau, then x tau is compact if and only if every open cover, rather basic open cover, that means what? An open cover consisting of elements purely from basis for a given basis, from the given basis, okay, admits a finite subcover. Okay, recall this fact, right? So how is it going to help me? Remember, for product topology, I already said, okay, these kind of things form the basis, right? Therefore, what can I assume? Now to prove the product topology is compact, I can assume let, okay, the ui cross vi, I in indexing set, be a basic open cover of x to y. Okay, then I have to show there is a finite subcover. So we want to know the existence of a finite subcover. Okay, right. Now that the idea is the following, and again, if you've seen my product topology lectures, you would know. Suppose this is how I write x, this is how I write y. Fix a point a in x, and let us look at this one. This is a. This is singleton a cross x, and similarly, this will be, suppose we fix a b, this will be x cross singleton b, right? And therefore the common point will be a comma b. That doesn't matter to me. Okay, yeah. Now notice that if singleton a cross x is homeomorphic to x, in fact it's enough. I will show that singleton a, oh sorry, y, did I say x? I'm very sorry. This is y. I looked at it. See, is homeomorphic to y. Singleton a cross y is homeomorphic to y. Okay. In fact, I am going to say this is a continuous image of, that's enough for me. Because since I know y is compact and the singleton a cross y is a continuous image of compact set y, this will, it turns out to be compact. Okay, so what all I want to claim is the following. What is it I want to claim? For any a in x, singleton a cross y is compact, and similarly for every b in y, x cross singleton y is compact. Okay, actually this is homeomorphic to y and this is homeomorphic to x, but you don't need that for compactness. But anyway, it will be a nice place to learn that kind of thing. Let me do that. So look at, fix a in x, look at the map. Okay, call it IA from x to, rather y to singleton x cross y. Yeah, and the map is y going to a comma y. Right, now IA is a map from the topological space y to the product space x cross y. I claim this is continuous. How do I know it is continuous? Now let's go back to the fact which I said. What is the fact I said? If I have a map f from z to x cross y product space is continuous if and only if each of the component maps are continuous, right? Now what are the component maps here? Component map is y going to a. This is a constant map, therefore it's continuous. The next map is y going to y. This is identity map, therefore it's again continuous. Identity map of y to y. Do you follow that? The first component map is from y to x. It's a constant map. Every y is mapped to singleton a. Second component map is from y to y, but that map is identity map, therefore it's continuous. Therefore, what is the conclusion? The conclusion is IA from y to x cross y is continuous, right? And what is IA of y? That is singleton a cross y. And what do I know about y? Compact. Therefore, what can I conclude about this? This compact. Similarly, I can conclude x cross singleton b is compact. Okay, pause, review, proceed. Yeah, now let us look at, so singleton a So let me write it as, okay, yes, singleton A cross Y is a compact subset of X cross Y, and my collection UI cross VI, I and I, this is an open cover, of course, of type 1 for singleton A cross Y, and this is compact, right? So using the compactness of singleton A cross Y, what do I know? This cover admits a finite subcover, right? Therefore there exists a finite set. Okay, now you notice that my writing, you remember whenever I write a finite set, I don't write something like x1, x2, xn or anything. I always write x comma I in some finite set. So you see that it's very useful. Okay, there is a finite set which depends on A because I fixed A, where it's a finite subset of A, so that UI cross VI I in FA is a finite subcover. Yes, right. Now notice that each UI, okay, A belongs to UI for all I in FA. Do you see that Y? Yes or no? How many of you see that? A belongs to UI for each I, right? Now, therefore, if you look at UI I in FA, this is a finite intersection of open set, therefore this is an open set, and A belongs to this. Okay, right? So call this U suffix A. Yeah, right. So when I say UI is a finite subcover, etc., what you are assuming is for each I UI VI intersection singleton A cross Y is non-empty. Do you understand why I am doing all these things? I said for each I in A, if A belongs to UI. How do I know that? Just try to think. These are the subtle points which are usually not explained. See, this is my singleton A cross Y, right? My open sets may be this. Notice that these are finitely many open sets, they seem to cover, right? But notice this fellow. Actually, all these fellows intersect this, but fellow, this is extra. So I can always add some UI cross VI unnecessarily, which does not intersect singleton A cross Y. Do you follow that? So what I am going to assume? So you choose exactly only a finite set so that each member should intersect. If it doesn't, it's useless. Okay, it's not going to do any service to form a covering for this set. Do you understand? Okay, please think, pause, review, proceed. So our assumption is there exists FA, a finite subset of I, so that for each I in FA, UI cross VI intersection singleton A cross Y is not empty, and UI cross VI I in FA is an open cover of singleton A cross Y. Is that all right? Now, since this intersects UI cross VI intersection singleton A cross Y is not empty, that means there must exist an element common to all. But any element here is of the form A cross A comma Y. Therefore, there exists y such that a comma y belong to ui cross ui, that means a must be in ui. Therefore a belong to ui for all I in fa. Okay, pause, review, proceed. Right, now my ua is intersection ui I in fa. Okay, and this is an open neighborhood of a. Now you see that, therefore what happens is, right, ua intersection y is contained in union I in fa of ui cross vi. Right, this is exactly what I showed earlier. Look at this picture. This is going to be your singleton a cross y, then a lot of finitely many, therefore this set, this will be your ua and this will be your y. So ua cross y is going to be contained in the whole thing. Okay, maybe this may be a better picture. So this is my ua. Okay, so this, keep this in mind, this is very important thing for us. Now let's look at, therefore for each a in x, okay, what I have found, there exists a finite set subset fa of I, okay, and open neighborhood ua of a in x, said that what happens, ua cross y is contained in I in fa of ui cross va. So again, if you want to have some picture, this is what happens. So this is my a, then I have ua cross this. Okay, there exists finitely many open sets, etc. And this may be my ua, another a dash, and this may be my thing. This will be my ua dash. Yeah, and there will be finitely many things which cover. Okay, I understood. Yes. So for now, let's look at, can you think of an open cover now? Let's look at ua, a in x. This is an open cover of x. Do you follow that? Yeah. Now what do I know about x? See, so far what we used was essentially the compactness of y. How did we use the compactness of y? We looked at the fiber singleton a cross y. Those things are called fibers. So we looked at the fiber. The fiber is continuous image of y. Therefore, we so far used only the compactness of y. Now we are going to use the compactness of x. Since x is compact, I know there exists a finite set a of x such that ua a in a is a finite open cover. Cover of x. Okay, pause, review, proceed. See, I am giving a lot of detail, that's why the proof looks slow, but if you go through that, you will understand better. Watch it second time, then you never have to review the proof. Okay, that is the beauty. When you understand itself, don't try to remember the proof, try to understand the proof. When you go through the proof first time, your emphasis should be understanding all the subtleties. Even if they are difficult, do that. Okay, then you will see the load on your memory will be less. Okay, you will be able to reconstruct the proof on your own. That is the beauty of learning properly. Okay, so what is the data now we have? So for each a in A, I have a collection UA, open set in X, so that UA cross Y, this is contained in UI cross VI, or I is very soon FA. Finite subset FA, right? And then I have a for each, sorry, X, and there exists a finite set A of X, so that UA, A in A is a finite cover. Just look at the picture, how many of you can see what you actually done? So for each A, okay, I have no, okay, this is covered by finitely many UI cross VI, okay, and there may be, this may be another UA, okay, this one is covered by finitely many, right? There are how many open covers of that kind? There are only finitely many covers. This is another UA. This is also covered by finitely many UI cross VI, right? And there are finitely many UI. So do you see the picture? So what is that you would like to claim? So what you would like to claim is the following. I hope all of you understand. So as A varies one, how many UAs are there to cover capital X? Number of elements in capital A. That's a finite set, right? For each UA, what do I have? I have UA cross Y, and that is covered by finitely many UI cross VI. Where do the I comes from? FA. What is FA is a finite set. Do you understand? Therefore, this is the collection UI cross VI, okay, right? I varies over FA, and where does A vary? A varies over capital A. Is a finite open cover for X cross Y. Pause, review. See, it's important to understand. Don't know, just try to memorize. The picture should already give you an idea what you are aiming at. Yeah, okay. First, it's an open set, each AI cross VA as well, and it's also finite. Why it's finite? How many elements will be there? See, for each A there are how many elements? FA elements, right? And A varies over this, therefore A varies over capital A. So the number of elements will be less than or equal to this. This is a finite sum. Why less than or equal to? Because UI cross VI may be in FA, and UI cross VI may also, the same I may be in some other FA dash also. You understand? So that is why you are writing as less than or equal to. So anyway, this is a finite sum. Okay, so it's an open set. There are finitely many open sets we have proved. What remains to be shown is it's an open cover. So we need only to show, is it an open cover? Is it a cover? What does that mean? I want to show whether X cross Y equal to union, okay, I in FA and A in A of UI cross VI. So how do I prove that? So start with any XY here. Therefore X belongs to X, right? But X is union of UA. Where does A come from? A comes from A, because this is a finite subcover, right? Therefore there exists an A in capital A, so that X belongs to UA, right? Now let's look at, now X comma Y therefore belong to UA cross Y. Yeah, but I know UA cross Y is contained in UI cross VI, I in FA. Therefore there exists an I in FA, so that X comma Y belong to UI cross VI, right? So what I have proved? I proved given XY there is an A in capital A and an I in FA, so that X comma Y belong to UI cross VI. So claim is proved. So that completes the proof. Please go through the proof. the okay, many people go through the proof very fast, okay, but without even geometry. So I took a lot of pain to explain the geometry and verified each and every detail, okay. And this is the way you have to learn proofs. Whenever you learn a proof, do not ever worry about whether you will recall the proof, whether you will be able to remember the proof, whether you will be able to write the proof in your exam. Don't do that. The correct approach to do is learn the proof as well as possible and keep reviewing once or twice. Okay, you will see with this trick 90% of the mathematics, okay, with the basic outline of the ideas, you will be able to reconstruct the complete proofs. Okay, that's how I do. Okay, so it's my secret. I told you those who are watching it regularly will know this is what I do all the time. For example, did you see that I wanted to say A belong to UI for every I in FA, okay, right? While I was explaining, I was thinking why it should be true, then I slightly modified the definition of FA. Did you see that? So it just shows I'm thinking, not simply trying to recall. I claim something happened, then I see how I proved it. Okay, I hope you all appreciate this. Okay, let's go back. So the first application, okay, let's look at R2, more generally Rn. Okay, this R2 is R cross R. This Rn is R cross n times. Right? So here we have the natural topology, namely is given by the Euclidean metric. Okay, what I used to call d2 of xy in terms of xi minus y whole squared I equal to 1 to n, and then take its square root. Yeah. Now I want to talk about, okay, I want to show any kind of rectangles. I will call it rectangle because it R2, okay, of the form AB cross CD, that is closed and bounded rectangle. So take a closed and bounded subset in the first factor and closed and bound another closed and bounded interval in the second factor, and so on. Take their product. In general it will be product A comma BI I equal to 1 to n. Okay, these are all called, this I will call n-dimensional rectangle, this will be just rectangle, right? I want to say they are compact. You will see it, you will say that it is immediate. Why? Because we had already proved that any closed and bounded interval in R is compact, therefore product of, and we had also seen product of compact space is compact, therefore this is a product of compact set, therefore it must be compact. Correct? Yes, that's it. What's the difficulty? The difficulty is, remember what did I write in the theorem? I was careful to write the theorem. This is the crucial word. With the product topology. But when you look at R2, okay, or Rn, the natural topology, if I don't say anything, that is supposed to be the natural Euclidean metric topology. So what is that I have to do? So I have to assure, okay, can we assure? So therefore question is, same as the product topology. Okay, once I know they are the same, then the argument I gave, any rectangle, closed and bounded rectangle is compact, is absolutely correct. Do you understand this subtlety? Yes, but that's very easy, because you may recall, if you have seen my earlier lectures or metric spaces, there are 3 different metrics usually I deal with on Rn. This is something to the mod xi minus yi. This is the standard. This is maximum mod xi minus yi. Right? And we had also seen how do open balls in D infinity metric look like. They look like squares, right? Therefore they are product of rectangle, product of closed intervals, closed and bounded intervals, sorry, open and bounded intervals. Yeah, and we had already shown that D1 topology is same as D2 topology, that is the topology induced by the D1 metric is same as the topology induced by D2 metric, and it's induced by the maximum D infinity or D max metric. All topologies are equal. These are all already seen. Okay. Yeah. And when we talked about open sets in Rn and one of the previous lectures, I have proved all these metrics induce the same topology in Rn. Right? Now let's go back. But therefore for D infinite topology, okay, the basic open sets are essentially squares. Okay, the basic open sets, that is basic open sets, are nothing other than balls. Here, that is D infinity balls in D infinity metric. They are nothing other than open squares. Okay, but for product topology, basic open sets are product of open intervals, right? And these two, so this is one basis product topology, let us say, and this is one basis with respect to infinite metric. Okay, and you know, two bases generate the same topology. When I dealt with the basis of a topology, I have proved, see, these kind of subtleties are never ever explained. That is why some of you may find my course is much tougher, but that gives you a lot of confidence. Okay, so the D infinity, this B product induce the same topology. Recall that this follows from, okay, look at the basis of the topology video. In that I have proved if I have two bases on X, okay, they induce the same topology for only give me any B1 in script B1 and any X in B1, then there is a B2 in script B2, so that X belongs to B2 and B2 is contained in B1, and similarly I. And similarly, give me any B2 in script B2 and any X in B2, there exists a B1 in script B1, so that X belongs to B1 intersection B2. So they will induce the same topology, and hence it follows the product topology, okay, on Rn is same as the metric topology on Rn induced by D infinity. But this metric topology induced by this is same as metric topology on Rn induced by D2. So what is the conclusion? So what I have shown is the product topology on Rn is nothing other than the standard topology, or the standard topology on Rn is nothing other than product topology. Do you understand this? These are the subtle things. You might have seen many textbooks will say Heine-Borel theorem after this, but the subtlety is very rarely explained. Okay, so let's come back. So what I have shown is any closed and bounded rectangle of the form product AIBI I equal to 1 to n in Rn is compact. Okay, this is the conclusion. So review proceed. Now we are ready for the kill. So do you remember we proved a Heine-Borel theorem for R? What did you prove? A subset A of R is compact if and only if it is closed and bounded. Notice that it's a necessary condition. Any compact subset of a metric space has to be closed and bounded, but the converse need not be true. But in the case of R, even the converse is true. That is, if you find a set which is closed and bounded, it is necessarily compact. Okay, that we proved it. Now we want to prove the analogous. So we want to prove Heine-Borel theorem for Rn. So a subset A of Rn is compact if and only if A is closed and bounded. So if A is compact, it's closed and bounded. That is very generally true for any metric space. Therefore, I don't have to prove. The only converse part I have to prove. Right? So how am I going to prove the converse part? Let us look at. So A is bounded, right? Suppose A is bounded and closed. Right? Now what do I know? That means there exists an M, or let us say R positive, so that for all x in A, norm of x, that is the usual Euclidean distance between x and 0, this is less than or equal to R. Right? What is this? This norm of x is summation xi squared to the power half. Right? Therefore norm squared is this. Therefore xi squared is less than or equal to norm x squared, but that's less than or equal to r squared. Therefore mod xi is less than or equal to r for all I. Do you understand that? Therefore for all I 1 to n, okay, mod xi is less than or equal to r. That means my subset A is contained in product of minus r to plus r, I equal to 1 to n times. That is, each ith factor is the closed and bounded rule minus r to r. Now what do I know about this? This is compact. Each of the factor interval is closed and bounded, and it is compact. And by, right, now by the theorem which you now proved, the product of compact spaces is compact. Therefore I know this is compact. Right? But what do I know about A? A is a closed set. Right? And this set is compact. Where this is compact? Since A is closed in Rn, it's also closed in this space. Right? Therefore this implies we already know a closed subset of a compact set is compact. Therefore A is compact. Okay, pause, review, proceed. If you want A to be closed in the subspace topology, it's again easy, because remember this is a compact subset in a metric space, therefore it will be closed. This A is closed in Rn, therefore A intersection this will be A itself, it's closed in the space. If you want, forget it. That's it. Okay. So let me see how much time I have. So I wanted to give some applications. For example, let's look at a sphere Sn, x in Rn plus 1, so that x dot x equal to 1. That is norm x equal to 1. Okay. This is compact because it's closed. Why it's closed? Because the map equivalent to summation xi squared, that is x dot x, this is continuous. Therefore f inverse of singleton 1, this is from Rn plus 1 to R. Okay, this is closed, and it's bounded because for each x in Sn, norm x is 1, therefore less than or equal to 1. Therefore Sn is closed and bounded, and therefore by Heine-Borel theorem Sn is compact. Sn is called the unit sphere on Rn plus 1, n-dimensional unit sphere on Rn plus 1. Okay, I hope you liked what we did. There are a lot of subtleties in the proofs which I took pains to explain, and do not be discouraged. Okay, stop whenever there is a PRP and review that and try to understand as much as possible. If you even understand 30, 40, 50, 60%, that's fine. Go ahead with the proof, then again revise, then you will understand completely. Yeah, that's what I do. Yeah, okay. It's not true that with the very first time I understand the proof. You don't believe? Believe me, that's true. We will meet again.